Okay, friends, let's try a few of these using Google for starters. When you multiply a negative number by a negative number, the result is bleh. Okay, well, let's just try some. Let's do negative 5 times negative 5. Google tells us positive 25. Okay, does that continue? How about negative 7 times negative 2? Positive 14. Huh. How about negative 1 million times negative 34? Positive 34 million. So it looks like it's positive. So then the question is why? And this, we hinted at this answer earlier in one of the videos a couple back. Why is a negative times a negative a positive? Well, let's think about it this way. Actually, you know what? Better yet, let's go to the board. Okay, friends, so I'm being intentionally general here by putting negative number times negative number. The implication is that whatever the number is, it's positive. So if you had a positive number times a positive number, then you get a positive result. Based on what we just saw, if we make one of those numbers negative, then the result of a positive number times a negative number would have to be negative. Putting another negative sign would have to be the opposite of that. So the single negative in a product creates a negative result. But another negative is the opposite of that negative result. Remember, negatives are opposites. That's a really helpful way of thinking about it. Negative numbers are opposites. So let's make a concrete example. Let's say we do negative 16 times negative half. First thing you can do is do the math on the numbers. Forget the signs. So 16 times a half is just 8. If it were just a negative 1/2 times 16, that would mean do negative 1/2 16 times, which would be negative a half, minus a half, minus a half, minus a half, minus a half. And that would end up being negative 8. But this is saying the opposite of negative 8, which would therefore be positive 8. Another way of thinking about it is half of negative 16. Well, if you cut half of negative 16, that's 2 equal pieces, which would be negative 8 and negative 8. So half of negative 16 is negative 8. But that's saying the opposite of that. So the opposite of negative 8 is positive 8. So if you think of it again in terms of opposites, negative numbers are not so terrifying. So when you multiply two negative numbers together, the result has to be the opposite of multiplying a negative and a positive. That makes sense? All right, let's try some more. Okay, my friends, so let's look at this number 24. We've seen that multiplying two numbers of the same sign, both positive or both negative, results in a positive, and different signs results in a negative. Does division follow these same sign rules? Well, let's goof around a little bit. Let's take a look. So let's say we know that negative 6 times negative 6 is positive 36. What if we do like negative 6 divided by negative 34? Okay, that's a positive number, right? There's no negative sign. That's a positive number. Okay, let's try another one. Let's try like a negative 67 divided by negative 98. Okay, that's positive. All right, so it looks like a negative divided by a negative might be a positive. We know a positive divided by a positive is going to be positive because that's old school. How about a negative divided by a positive? How about something like negative 345 divided by 45? Okay, so a negative divided by a positive is a negative. Is that true in all cases? Well, let's see. Negative 125 divided by positive 748. Okay, so it looks like a negative divided by a positive is a negative. So far, the rules are being followed, right? A negative times a negative is a positive times a positive is a positive. It looks like a negative times a positive is a negative. What if we switch the sign to the denominator? Does it stay negative? Okay, so it looks like it does. So it looks like negative times negative is positive. Negative divided by negative is also positive. Positive times positive is positive. Positive divided by positive will be positive. So if the signs are the same, division is a positive result. But if the signs are different, it's a negative result. Why? Oh, you know what? The best way I think to look at this, let's go back to the board. Okay, as I was reading our answers to that number 24, I realized something. We've already answered this in previous videos in this class. Why does division follow the same rules as multiplication? And the answer is because division can be written as multiplication. Think about why. Think about how, why. Let's look at a simple example without negative numbers. Suppose you're doing 16 divided by 2. Divided by 2 can be rewritten as, now, I'm not saying that you would do this, but it can be rewritten as 16 over 1 times 1 over 2. We're kind of undoing the math we did with dimensional analysis a couple weeks ago. So if you take a look at this and read it a different way, division by 2 is the same as multiplying by a half. Now you learned this at some point, many, many years ago, that when you divide by a number, it's the same as multiplying by a reciprocal. Now when you did it back then, it was probably under the guise of some silly fractional question like 18 divided by a third. But still, that's, even though it's silly, it's still the same because you can rewrite that as 18 over 1 times the reciprocal of 1/3, which is 3 over 1. So division by a number is the same thing as multiplication. And that's why number 24 makes sense. Because as soon as you take away this fictitious example here, there we go. Sorry, I just did a 360 looking for my eraser. And let's stick a negative sign in here. 16 divided by negative 2, for example. Why should that be a negative result? Well, because rewriting it this way, you're multiplying a positive times a negative, which we've already established. A positive times a negative is negative. So it makes perfect sense that division should follow the same sign rules as multiplication, because division is another way of expressing multiplication. Okay, one more to do here. Back in 21, we noticed when we multiplied two numbers with different signs, the result was negative, whether the positive or negative number came first. That's true, because you can always think of multiplication either left times right or right times left. As a matter of fact, that's actually got a name, which you don't have to know, but it's a fun name. It's called commutative or commutativity in mathematics. You can multiply in any order. 2 times 3 is the same as 3 times 2. And that also goes for negative numbers. It's one of the nicer things. So order does not matter for multiplication, so long as you're only doing multiplication. So this question asks, which operations would it matter for? Addition, subtraction, multiplication, or division. So we know it doesn't matter for multiplication. So I'm going to go ahead and just cross that one out. There, we know it doesn't matter for multiplication. Let's check addition, subtraction, and division. And we're going to use our good buddy Google to do that. All right, Google. All right, so let's do some additions. Let's add some negative numbers and positive numbers, or negatives and negatives, a couple different ways. So we'll do like negative 8 plus 6. And we get negative 2. All right. Now let's do 6 plus negative 8. And we get negative 2. Okay. Let's do some different ones here. Let's do two negatives added together. So let's do like negative 18 plus negative 6, which gives me negative 24. And now let's switch the 6 and the 18, or the negative 6 and the negative 18. Negative 24. So it appears that addition is also commutative. Okay, all right, I'm buying that. So we can come back to our notes and we can cross out addition. We don't need to worry about addition. How about subtraction and division? All right, let's go back and look at that. let's subtract some numbers. So let's do 7 minus 6. 7 minus 6 is 1. How about 6 minus 7? Ooh, 6 minus 7 is negative 1. Okay, so it matters for subtraction. I mean, we just found an example, which means it matters. And let's look at division. Let's use the same numbers. Let's do 6 divided by 7. And 7 divided by 6. There's a difference there too. So it sure looks that it matters for subtraction and it matters for division. And I guess the question then is why? Why does it matter for those two, but it doesn't matter for the other ones? I think I have an explanation. Let's go to the board one more time. Okay, friends, I was agonizing over this question. What's the best way to explain why it doesn't matter when you switch numbers with a multiplication problem or an addition problem, but why does it matter with division and subtraction? So I decided, let's use our old dimensional analysis unit-driven mathematics to explain, using some examples which I think will clear things up. So let's start with something like 2 feet times 4 feet. So this is something kind of like we did a couple weeks ago. Now we know what that answer is. It's 8 square feet. But let's visualize it. Let's visualize it as 2 feet. I'll try to draw this to scale. I think I can. Yeah. So that's about a foot. And that's about a foot. So there's 2 feet there. And then 4 feet is going to be twice as wide. That'll take us just about to the end of this board, I think. Okay, if I cut that up into feet. It's not perfect, but it gets the idea across. Yeah, 4 feet up here. So you have 8 square feet. 8 square feet. I'm curious how close I came with some of these square feet. I did okay. That one's not very good. I did okay. Sorry. The East Coast in me wanted to check that out. Okay, so that's 8 square feet. Because that's a square foot, that's a square foot, square foot, square foot. Why would it not matter if you looked at it as 4 feet times 2 feet? Why does it not matter if you swap out and put the 4 feet in front or the 4 feet second? And I think the idea is when you're left with the final result of 8 square feet, it really doesn't matter if you call it length times width or length times width, because the end result was built up of the 2 component pieces. And I know that might not be super satisfying to you. You might say, well, that seems just like a trick of English. But it's not really, because you may have noticed that both multiplication and addition seem to have the switchability, but division and subtraction don't. And what do multiplication and addition have in common? They both build things up into a total as opposed to starting with a total and breaking it down. So here's an example of multiplication switching not mattering. And this same argument will work for any bit of multiplication. So it doesn't matter if you do 4 times 2 or 2 times 4, or 4 feet times 2 feet, 2 feet times 4 feet. The order that you multiply in doesn't matter. Let's take a look at addition. Okay, let's do 1 foot plus 3 inches. Now the first thing you have to do is make sure you get the same units, because you can't combine 3 plus 1 and call it 4. We have to have the same unit to combine using addition, or subtraction for that matter. So I'm going to call 3 inches 1 foot plus 1/4 of a foot. So if we envision what that looks like, imagine what a foot looks like. That's about a foot, right? That's 1 foot. And then 1/4 of a foot is going to be 1/4 of that. If you bump those two things together, you're going to end up with 1 1/4 feet. Now, would it matter if we had added the quarter foot on this end versus this end? Well, I mean, you could maybe visualize it as being maybe shifted over a little bit, but isn't the end result the same? And again, addition, like multiplication, is a build-up operation. The end result appears to be completely independent of the order you put the individual components in. Now that, again, this might not feel satisfying to you because it's not really a proof, it's just demonstration. And this is one of the things we'll learn about in 105 going forward. Proving something is true is extraordinarily challenging. As a matter of fact, these properties are one of the hardest things I ever had to prove in my undergrad years as a math major. Prove that addition and multiplication are commutative. But it's really easy to show why division and subtraction aren't. Let's take a look at that now. Okay, so here's two unitless math problems, which I told you we were going to use units, but I want to start with unitless to show you the difference here. 10 divided by 5 and 5 divided by 10. It's not too hard to put those into a calculator and show that that equals 2 and that equals a half. Here's where it gets easier. Imagine taking $10 and dividing it amongst 5 people. Each person gets $2 per person. Now imagine taking $5 and dividing it up amongst 10 people. Now everybody only gets half a dollar per person. Now why is that? Why is that? Because division is breaking things down. And depending on where you're starting and how many pieces you're breaking it into, that tells you how big the end result is going to be. If you start with a different amount and break it into a different number of pieces, you're going to end up with a different overall net result. Because it's a breakdown operation, the end result is going to be different. Let's look at subtraction. The exact same thing happens, but let's take a look. Okay, 3 yards minus 1 foot. Again, just to kind of get us thinking about this, I'm going to change 3 yards to 9 feet. 9 feet minus 1 foot. So if you measure something that's 9 feet long and cut a foot off, you're going to have 8 feet left. Pretty straightforward. How about 1 foot minus 3 yards? Well, as soon as you look at it that way, you realize, wait a minute, you can't do that. If you're talking about something like wood, for example, you can't start with a 1 foot piece of wood and then cut 9 feet off of that. If you do the math problem, 9 minus 1 and get 8, 1 minus 9 will be negative 8. So it turns out they're opposites of each other. So subtraction, just like division, is a breakdown property. It starts and then removes. And unless you're starting and removing the same amount, the end result is going to be different, just like in division. I hope that made sense.